We're going to do something really fancy here. It's called linearization. And linearization is a way of getting a statistic out of a non-linear equation. So let's just say I drop a ball. It starts from rest. The delta y is going to equal to v0t plus 1/2 at squared. The v0 is 0. So it ends up just being 1/2 times the acceleration, which is g, times t squared. So if we take data on this, we can find g. All right? And yes, we know g is generally near the Earth's surface at a certain value, but we want to find it. We want to measure it. So we drop a ball and we find in 0.25 seconds, it goes 0.31 meters, and we do all this stuff. Maybe we do it off of video analysis. And we find for every time how much displacement it has. Okay, so then we graph that, and we got a problem. We graph the data, and by the way, notice when we take data, it's there can be some uncertainty in there. There can be some bad measurements in there. So it's very important that when we take a bunch of data, we want to find a statistical way of characterizing the relationship. That's what we're going to be doing to find that g. So there's a relationship between delta y and t, and it's exponential. So we take our data, we do a trend line, a best fit line, and actually we can use an automated approach like graphing it in Excel or Google Sheets, and we can get statistics off that. But something very, very common in AP Physics C is to give you data and say, what would we need to graph to get a linear graph that would give us a slope that will allow us to find this certain thing, g in this case? Well, what we want to do is, if you think of what a linear graph gives you, and this is for something very different, I just made up these numbers. Okay, if we have a linear graph, we can get the slope. It's real easy to find statistic, right? If we can graph this on graph paper, very easy to figure out what the slope is. So if that slope is some function of the thing we're after, it'd be really easy to find the thing we're after. So what we want to do, any type of linear equation is going to look like this. What we graph on the y-axis is m times what we graph on the x-axis. And that m is the slope. So what we want to do is we want to take things we can plot and put them on the y and the x. They may not be the things we measured. They may be functions of the things we measured. So for example, instead of delta y graphed on the y, we might want y squared, delta y squared, or square root of delta y, or 1 over delta y, but some function of the variables, okay? I'll show you, it becomes much clearer when you see what we do. And then the slope is a function of whatever it is that we want. Here's how it would work with our example. Delta y equals 1/2 gt squared. How can I make that look like y equals mx? Well, I could graph delta y on the y-axis. I could graph t squared on the x-axis. Then the slope, m, would be 1/2 g. So let's just say if the slope was 4, then that equals 1/2 g. G would equal 8. So we could find g from that. This t squared is the trick. Instead of graphing t on the x-axis, we graph t squared. So we actually have to, in our data, we have to make a new column. And this is what that would look like. We had the time and the delta y, right? But now we're going to add this new column, t squared, which for every entry in there, we're just going to take 0.25 squared is 0.0625, 0.5 squared is 0.25, etc. Really easy to do in a spreadsheet. I would just do in that top line there, equals, and then I'd click on the cell next to it and do squared. And then fill it down and automatically would populate that whole thing. So on the x-axis, I graph that t squared. On the y-axis, I graph that delta y. And when I do that, I end up with this graph. This is not real data. I made up the data, but this is actually if I graph t squared versus delta y for the data we had at the beginning. And I do a trend line, and if you look up top, I found the slope. So if you label that graph with the equation, it says 4.69x minus 0.0643. That's just a y-intercept, just basically because the data is not perfect. Doesn't perfectly go through 0. So 4.69 is the delta y divided by the time squared. So I end up with the slope 4.69 is equal to 1/2 g, right? That's that m in the y equals mx. 1/2 g is equal to the slope that I found, 4.69. So g is equal to 2 times 4.69, which is 9.38 meters per second squared. Okay, let's do another example here. We'll take resistance. Resistance is equal to resistivity times the length of a wire divided by the cross-sectional area. You don't need to know all that. All we need is an equation. And we say, okay, the area is a constant. So we did an experiment on a constant area wire. And what we did is we changed the length and we measured the resistance. And we want to find rho. Well, it's pretty easy to do here. There's our data. Well, we just take on the x-axis L over A, and on the y-axis R, and the slope will be rho. So we create a new column, and that's L over A. So we take 0.2 divided by 0.0024, 0.4 divided by 0.0024. We'd put it in that column. Then we'd select those last two columns, and we'd graph, and the slope will end up being equal to rho, exactly equal to rho. Remember in the last example, we had 1/2 g was going to be the m. In this case, rho itself is the m. I don't even have to do anything crazy. So let's do a little more complicated example. This is the period of a pendulum. And so it's equal to, we know the equation is 2 pi square root of L over g. L is the length of the pendulum. So we measure the length and the period, just the length, measure the period, and we want to find g. So if we had a table of L and TP, we could do this a number of different ways. Again, we want to make it look like y equals mx. So the first way we could do it is this way. We could have TP as the y-axis, square root of L, we'd need a new column for the x-axis there, and then 2 pi over square root of g would be the slope of the line. So we'd find that slope, and then we'd have to do a little algebra to figure out what g is. Another thing we could do is we get rid of those squares. We could say, let's do TP squared. And so if we square both sides of the original equation, that's 4 pi squared over g times L. So we graph L on the x-axis, TP squared on the y-axis, and the slope would be 4 pi squared over g. Now sometimes it makes it easier if you can just have the slope be the thing you're looking for. So if I rearrange this equation so the g was up top, I could get something like this. This would come from squaring both sides, multiplying both sides by g. And so then I can, for this one, I want g to be the m. So TP squared would be my x variable. 4 pi squared L would be my y variable. So how is this going to look on an AP problem? On an AP problem, what they're going to say is somebody makes these measurements. Here's the data. What could you plot as y and x to yield a straight line equation that would allow you to calculate such and such a variable? Okay, so you would actually have to say what variables you would graph. Then you would actually have to create a new table, a new column, or maybe even 2 new columns. If you look at that last one, that's 2 new columns. And then finally, you would have to graph it, do a trend line, find the slope, and calculate the variable that you were looking for.